Okay, shall we start analog electronics? Very good evening, all. Please say good evening. I don't know how many of you joined yet. Okay, let us start the session. Fine. See, we are going to start the next subject. See, that is simply called what? Analog electronics, right? So already we designed the basic circuits like we saw some switches in power electronics, very important, right? And we saw some type of switches in digital electronics. Like that, in analog also we are going to learn some basic switches. Like in analog, especially we are going to discuss about in high frequency how your switches are going to react, what type of switches we are that is looking for, like what is the basic of operational amplifier and what is the basic of oscillators, how we are going to design oscillator circuits and operational amplifier, and how basically our transistors are working to amplify these signals, and how our MOSFET is working, field effect transistor, right? And we are going to learn some basics of diodes also, right? Yeah, so let us start. There are many things to learn. We will go from the basics, and then we are going to learn the basics of diodes, and then we are going to discuss about the basics of transistors, and then we are going to discuss about the basics of MOSFET. At last, we will discuss about what I can say feedback amplifiers, oscillators, operation amplifier. There are many things to do, right? We will see all those things one by one, right? Okay. Now, what I told you, this time I don't want to cover the engineering service exam syllabus at all. We are going to cover only our state exams and the central exams, except ESE, engineering service exam, right? So in engineering service exam point of view, we have to learn some basics of electronic devices and circuits. Yeah, that part is actually that is the core of EC, electronic communication, right? We should study something about the basic fundamental properties of intrinsic semiconductors and extrinsic semiconductor, right? Yeah, anyway, let us coming to the syllabus directly. I'm just going to cover only electrical engineering syllabus, right? In your free time, if you want to know the basics of intrinsic semiconductor and extrinsic semiconductor, right, you can just google it, and you can there are many files are there, you can refer, right? And you can also refer some local author book, if that is enough, right? If you have any local author books for electronic devices and circuits, you just go through it to get some basic ideas, right? Anyway, I'm giving some basic fair of ideas that it should be required to design our switches directly. Okay, fine. Now what we are going to design, we are going to design some basic switches, right? For that, first we are going to learn about the types of the material that we are going to use, right, in analog electronics. Basically, in analog electronics, right, especially there are three types of materials are there in this universe. One is simply called conductor, and another one is called insulator, and another one is called semiconductor, right? Now, what type of material that we are going to choose to design the analog electronic switches, right? Especially, why it is called analog electronics? Analog, we are going to discuss about continuous signals and switches, right? That's all. There are no more things to discuss. We know the meaning of analog, and we also know the meaning of what electronic switches. We are going to design electronic switches, right? Usually, if you observe, electrical switches ratings are very high, whereas in electronic switches ratings are very what I can say very less, right? That is, we are going to design some type of applications, like how to use the diodes in various applications, and how to use the transistors, or how to design the transistor from the diode, and how to amplify the signal, like electronic applications in the sense headset, like how to design the headset, how to amplify the signals, how to design the speaker, how to design the frequency oscillators like CRO, right? All are electronic devices. Like in mobile, right, we are going to whichever the applications that we are using as electronic, that electronic switches are going to be designed with the help of analog only, right? So we are going to learn some basic part of the switches that are going to be help us to design analog applications, right? That's what I can say, electronics applications, right? Yes, so let us start. So basically, I said there are three type of materials, right? One is insulator, second one is conductor, and the third one is what? Semiconductor, right? Out of these three material, which material we are going to use, or we are going to prepare to design the analog switches? The material that we are going to choose here, it is simply called semiconductors, right? So directly totally we are going to discuss about. Sir, video is loading, huh? Guys, please let me know, do you have any interruption? Is class is going good or not? Please let me know, is there any problem in class, whether the class is going good or not? Yeah, I think okay. Class is going good, right? Okay, let us start this subject without wasting our time. See, totally we are going to discuss about what I can say three type of materials, right? First one is what? Conductors, right? First one is conductors. Second, we are going to discuss about semiconductors, right? Of course, we are going to discuss about semiconductors. At last, we need to discuss about what? Insulators, right? We need to discuss about insulators, right? Out of these three materials, for which material we are giving priority in analog device, right? We are going to use semiconductors to design analog electronics, right? Yeah, semiconductor in the sense it will conduct partially up to a certain voltage. Your device won't turn on, right? After a certain voltage it will turn on, right? That is called semiconductor. Whereas in conductor we can say there are, that is the amount of electron volt, right, that it should be required to move the voltage from one point to another point is zero electron volt. In case of conductors, right, the amount of voltage that it should be required to move the electron from one point to another point is zero. It means just by small amount of electromotive force we can experience the current flow in case of conductor. That is simply called conductor. Whereas in case of semiconductor devices, right, the amount of electron that it should be required is, that is electron volt, right? We are just going up with a 1 electron volt average value, right? Minimum 1 electron volt should be required to move the electron from one point to another point in case of semiconductor devices. If you are looking for insulator, around it should be 6 electron volt, right? So totally we have three type of material: conductors, semiconductors, insulator. Whereas priority will be, anyway we are going to design the analog switches with the help of semiconductor, right? So to move the free electron, see, first of all, what do you mean by free electrons? Free electrons in the sense, first tell me what is the definition for current. Flow of electron is simply called current. It means flow of electron. Free electron, I am randomly, right? Free electron in the sense, that is what I can say simply, it is randomly already moving from one point to another point. Just by applying some external field we can shift the electron from one point to another point. Once your electrons are started traveling, then that is called what? That travel is simply called current flow. But we know usually we are taking, our conventional is what? Positive direction is our conventional. Electrons are simply treated as negative charges, whereas holes are being simply treated as positive charges, right? So here we are taking positive current. Positive current in the sense we are simply following the direction of holes, whereas negative charges in the sense, negative charges are traveling in the opposite direction to positive charges, right? Our conventional direction is positive current. Positive current will follows positive charge carriers, right? So current will always opposite to the direction of electron, that is electron flow. Why? Because electrons are simply called negative charges, whereas current is positive current. Positive current follows positive charges, right? So electrons and the current flow are will be, that is, if electrons are traveling in this direction, in opposite you can experience the positive current. Guys, don't think that why your current is traveling in the opposite direction. I am just asking you how many charges are there. There are two type of charges. One is negative charge, another one is positive charge, right? If you are traveling, that is, if you are just following the path of positive charge, then the corresponding current is called positive current. If you are following the path of negative charge, then the corresponding current is called a negative current. it's over, right? But we are traveling what? We are traveling along with the positive charge, our conventional, right? So positive current will always be opposite direction to the negative charges, right? So that's why your electrons and positive current are always opposite to each other, right? Now coming back to the conclusion, in semiconductor, to make free electrons, right, to let the free electrons to move from one point to another point, at least I'm in need of 1 electron volt, right? Whereas in case of insulator, it should be what? 6 electron volt, right? Yeah, whereas in conductors means what? Already free electrons are readily available. Whereas here we are creating the electrons. Here also we are creating the free electrons, right? Your electrons are tightly bound with the atoms, right? Your electrons are tightly bound with the atom. In case of insulator and semiconductor, with the help of some external force, we are trying to move the electron from one point to another point. That is simply called what? Electrons, right? That is what I can say, current, right? When your electrons started moving from one point to another point, is simply called current. Okay, so these are the basic classification of your conductor, semiconductor and insulator, right? Fine. So let us continue. Anyway, we are going to discuss about semiconductor materials only. We are going to discuss about semiconductor materials, right? I think class is going good. If you have any problems, please let me know, right? Class is going good, yes, please let me know whether the class is going good or not. Yeah, I think many of you joined, right? Yes, let me continue. I hope now we can continue with it. One second. No, just let them to go. Yeah. Okay, fine. Let us continue. This is all about conductor, semiconductor and insulator. We know the classification now, right? So let us continue. Now let us take the semiconductors. Let us take the semiconductors and let us discuss about the properties of semiconductors, right? Okay. In semiconductor, if you observe, there are three type of materials we are going to use, right? First, we are going to discuss about silicon. Second, we are going to discuss about germanium, and then we are going to discuss about gallium arsenide, right? Gallium arsenide. Sir, there are three type of semiconductor materials are there, right? So these are the materials that we are going to use to design what? Analog electronic switches, right? Fine. Now, semiconductor, silicon, right? Germanium and gallium arsenide. Out of these three materials, first priority will be given for silicon and germanium. Priority will be given for silicon and germanium. We are not giving priority for gallium arsenide. We are not giving priority for gallium arsenide, right? So there are three type of semiconductor materials are available, but priority will always be given for silicon and germanium. We are not giving that much priority for gallium and arsenide. Sir, why we are not giving priority for gallium and arsenide? Actually, the thing is, just now I had been told you, in order to create the free electrons, right, in semiconductor material, at least I'm in need of 1 electron volt, right? Whereas if you observe the silicon, exactly I can say, to create the free electrons in case of silicon, I'm in need of 1.2 electron volt approximated value. And similarly for germanium, I'm in need of 0.7, that is approximated electron volt. Whereas in case of gallium arsenide, I have to spend nearer 1.85 electron volt approximately. So when we are comparing these three materials, right, your gallium arsenide usually required more electron volts to create the free electrons. So when we are comparing these three type of materials, priority will not be given for gallium arsenide because of this requirement of high electron volts to create the free electrons, right? So we are not giving priority in case of analog electronic switches. But you know, in our modern technology, right, in modern technology, modern means CMOS technology, right? Channel MOSFET. In channel MOSFET, priority will always be given for gallium arsenide. Sir, why we are giving priority in modern MOSFET? Why? Because the reason is, in case of gallium arsenide, the switching speed of the gallium arsenide is very high, right? Switching speed because of the mobility. When we are comparing the mobility of these three people, mobility of gallium arsenide is very, very high. Mobility in the sense movement, right? Movement. Freely we can move, right? So here in gallium arsenide, listen, Though your gallium arsenide is required more electron volts to shift the electron from one point to another point. Though it's required more electron volt, right? But it's required, that is, it is easily moved from one point to another point, right? Movement of the electrons is freely, it will go from one point to another point when we are comparing your gallium arsenide with the silicon and germanium materials, right? So what is the conclusion here? So the conclusion is, when I am comparing your gallium arsenide with the silicon and the germanium, switching speed of the gallium arsenide is very high. So in nowadays, that is CMOSFET we will see, discuss about NMOSFET and PMOSFET at all, we will see in future. So in PMOS and NMOSFET at all, priority will always be given for what? Gallium arsenide, right? So anyway, so what is the conclusion here? To design the analog switches, we are going to give priority for silicon and germanium in the requirement of voltage point of view, in the requirement of switching point of view, switching speed point of view. Gallium arsenide will be used in order to design the, what I can say, CMOSFET, right? That is NMOS and PMOS, they are lying under CMOS, that is complementary MOSFET, right? Fine. So let us C denotes complementary MOSFET, and there are N MOSFET will be there, P MOSFET will be there. In all type of MOSFETs, priority will be given for gallium arsenide to design the field effect transistors because of the high switching speed. I hope things are very clear now, right? Okay, let us coming back. So let us take the silicon and the germanium. Though silicon and germanium materials are prepared to design the analog switches, out of the silicon and germanium, many of you guys had been studied already. Sir, siliconium germanium is, that is silicon material is often prepared to design the analog switches. We are not giving priority for germanium. Why, sir? Though we are having two different materials here, okay sir, we are selecting out of three, two materials have been selected. Now out of two, one material only will going to be selected to design analog switches. Why, sir? What is the beauty of your semiconductor, that is silicon material, when I am comparing it with the germanium? Right? Let us see. When I am taking the silicon material, it has lot of advantages. Right? Guys, can everyone hear my voice? Whether the class is going good or not? I told you, please post it in the comment section. Do you have any problems with our class or signal issues? Please let me know. Okay, let us continue. Let us discuss about silicon material. Actually, in silicon material, first I need to talk about the temperature range of the silicon material. The withstand ability of your silicon material is 200 degrees Celsius. Is 200 degrees Celsius. That is the withstanding ability, temperature withstanding. It means up to 200 degrees Celsius, there is no issues with their silicon material. It will accept the temperature and it won't change its property. Whereas, if you are observing the germanium, temperature of the germanium is what? It is only 100 degrees Celsius, right? So the temperature and that is withstanding ability of the germanium is only 100 degrees Celsius. So when we are comparing these two material, priority will always be given for silicon first in the temperature point of view. And the second thing is, often in future I am going to talk about a term is called reverse saturation current, right? I am going to talk about a term is called reverse saturation current, right? Reverse saturation current. In future, I am going to talk about a term is called reverse saturation current, right? Reverse saturation current, I can also write the formula. It can be written as, that is current through the diode. In general, it can be written as ID is equal to I naught into e power voltage drop across the diode divided by ideality factor into thermal voltage minus 1, right? This VD by eta times of VT lies in the power of exponential term E. Okay, this term is lies in the power. So this is minus 1, that is the whole term, right? Whole minus 1, we can write like this. Okay, fine. I hope things are clear now. This is the general formula to obtain the current through the diode, right? So let us continue. Actually, I am talking about what? Reverse saturation current. Here, this I naught stands the reverse saturation current, or some people are writing it as I naught sat. Reverse saturation current, right? So reverse saturation current, that is off state saturation current. Almost your device is turned off, but some current is started flowing into the circuit, right? That is called reverse saturation current. We are calling it as reverse saturation current. We are calling it as reverse saturation current. Exactly, right? Sir, what we are trying to conclude here, actually, what do you mean by reverse saturation current? It means, listen guys, நீங்க diode வந்து ஆஃப் பண்ணிட்டீங்க. Diode வந்து என்ன ஆயிடுச்சுன்னா ஆஃப் ஆயிடுச்சு. ஆனால் டயோடுக்குள்ள சம் கரண்ட் ஃப்ளோ இருக்குது, தட் இஸ் கால்டு வாட்? லீக்கேஜ் கரண்ட், ரைட்? இப்போ டயோடு வந்து ஆனில் தான் இருக்குது, ஆனால் ரிவர்ஸ் பயாஸில் இருக்குது. ஆக்சுவலாக ஒரு டிவைஸ் வந்து ஆஃப் ஸ்டேட்டில் இருக்க வேண்டிய இடத்துல அதுலேயே சம் லீக்கேஜ் கரண்ட் போயிட்டு இருந்தது அப்படின்னா we are simply calling it as what? Saturation, that is reverse saturation current, leakage current, right? So in this reverse bias, actually your diode has to turn off. There are two type of bias we are going to talk in future. What do you mean by bias? What do you mean by forward bias? Everything I will discuss, right? So first thing, in our diode there are two states. One is called forward bias and another one is called reverse bias. right? So in forward bias your device will turn on, in reverse bias your device will turn off, right? So here, whereas in reverse bias actually your device has to turn off, but instead of turning off the device, there you can experience some type of reverse saturation current. It means through the diode you can experience the current in the opposite direction to the normal, that is from the normal direction. Normally your current is going from anode to cathode in case of diode, whereas in the reverse bias you can experience the current flow in the opposite direction, and that current will be in nanoampere, and it will also will be in milliampere. Now there are two cases, right? It might be in nanoampere, right? Wait a minute, it is in microampere and nanoampere, right? And sometimes it will also be in milliampere, it will also be in milliampere. Now this milliampere microampere could be available in case of silicon material. If you observe, in case of germanium it will be in nanoampere, right? Sorry, I think wait a minute, I had been reversed. This is silicon, this is germanium, right? Sorry, forgive me. Yeah, so the thing is what, in case of silicon material current is in nanoampere, almost it is equal to 0. Listen, actually in the reverse bias your device has to turn off, but your germanium is carrying the current in microampere or milliampere. This is not acceptable current, right? Actually in the reverse bias what, your current has to be 0, but I am getting what, your current is in microampere, or sometimes it will be, there might be a chance of getting your current in milliampere also. So this is not acceptable, this is not acceptable. Whereas in silicon your current is almost in nanoampere, which is equal to what, 0. This current is equal to what, 0 ampere, right? Yeah, so the conclusion is what, reverse saturation current in case of silicon, right? So the off state reverse saturation current of the silicon material is always less than the value of off state reverse saturation current of the germanium. So for which material we are giving priority now? Priority will always be given for silicon. Why? Because in reverse bias almost its reverse saturation current is equal to 0. Clear? That is the another reason why we are giving priority for silicon material. Clear? Yes. So let us take, there is one more reason why we are going up with the silicon material, right? So let me take this is temperature, and the second we had been discussed about saturation current, right? Next let me discuss about cut-in voltage also, right? Now what do you mean by cut-in voltage? That is the famous question, right? That is the famous value that we all know, right? What we know, in case of silicon material cut-in voltage, right? Cut-in voltage, it is also called potential barrier, right? That is called barrier voltage, right? So we are also calling it as what, barrier voltage, right? So this cut-in voltage should be equal to, in case of silicon material it is 0.7 voltage. For germanium, right, your cut-in voltage should be equal to, that is it will be equal to 0.3 voltage, right? So what is the another conclusion here? Sir, when I am comparing silicon with the germanium, cut-in voltage of the silicon is greater than the value of cut-in voltage of germanium. So in the cut-in point of view, priority once again will be given for silicon material only. So totally we saw three reasons, right? First we had been discussed about temperature, right? Temperature, and the second thing is another reason is what, we had been discussed about reverse saturation current. In case of silicon material reverse saturation current is very less when we are comparing it with the germanium material. Third we had been discussed about cut-in voltage. In case of silicon material cut-in voltage is 0.7, whereas for germanium it is equal to 0.3, right? Yes. So let us continue. Okay sir, these are all the reasons why we are going up with the silicon material. Now after selecting the silicon material, now I would like to talk about few more basic terminologies, right? So let us discuss about intrinsic and extrinsic materials, right? First of all, what is the difference between intrinsic and extrinsic, right? We have to understand, that is intrinsic and extrinsic, right? Extrinsic, what is the difference between intrinsic and extrinsic material, that is intrinsic, right? So what is the difference between these two guys? Actually the difference is intrinsic in the sense we are having purely semiconductor material. Your material is purely semiconductor, right? Whereas here we are also using some doping in the sense purely semiconductor material, right? Purely semiconductor material will be combined with some type of other doping, right? So we are also doping, that is impurity, right, will be added. We can say impurity will be added to improve the characteristics of the material, right? So here we can say the example is, we can consider phosphorus, right? We can consider that is arsenium, right? So there are many materials are there, right? I don't want to go with these things at all. Let us coming back, in case of intrinsic, I can say some example, that is silicon material, right? In your free time you can read all these things, right? Some boron will be there, phosphorus, antimonium, some bismuth will be there, right? We can consider many material in case of extrinsic. First of all, what is the difference between extrinsic and intrinsic material? என்ன டிஃப்ரென்ஸ் அப்படின்னா, இன்ட்ரின்சிக் மெட்டீரியல் அப்படின்னா பியூர்லி ஒரு செமிகண்டக்டராக இருக்கும். இதே வந்து எக்ஸ்டென்சிக் பற்றி பேசணும் அப்படின்னா, மெட்டீரியல் வந்து எப்படி இருக்குன்னா பியூர்லி செமிகண்டக்டர் கூட சம் டோப்பிங், ரைட், இம்ப்யூரிட்டி வந்து ஆட் பண்ணுவாங்க எக்ஸ்டர்னலாக. லைக் இப்போ நம்ம கோல்டு இருந்து பியூர் கோல்டாங்க நீங்கள் வாங்குறது, நோ, வி ஆர் பையிங் ஜுவல்ஸ், ரைட்ஸ், நீங்கள் வாங்குற ஜுவல்ஸ் வந்து பியூர்லி கோல்டா, No, that is not gold, right? Pure gold வச்சு உங்களால் எதுவும் செய்ய முடியாது, right? So we are adding what? Some other type of materials, that is impurity, will be added with the gold such that we can mold, right? Whichever the designs that we want, we can design it after adding some impurities, right? So that is how we are designing the jewels. In the same way, in order to improve the characteristics of some materials, right? Like you might be increase the electron content, that is the concentration, or what I can say, holes concentration. இப்போ எனக்கு ஒரு மெட்டீரியல் இருக்கு, அந்த மெட்டீரியல் வந்து 1000 எலக்ட்ரான்ஸ் தான் இருக்கு, but I would like to increase the strength. ஒரு 10,000 electrons வந்து நம்ம கொண்டு வரணும் அப்படின்னா, we are adding what? Externally we are adding some another type of material, right, which is having more electrons such that the number of electrons or concentration of the electrons will be increased. That is simply called extrinsic process. It means that is purely semiconductor material will be added with some impurity, right, in order to increase the doping concentration of the material, right? So that is the difference between X and intrinsic materials. I hope things are very clear. Yes, let us continue, right? Let us continue. Anyway, we are going to design our PN junction materials at all with the help of what? Intrinsic material, that is our silicon, right? That is purely what? Purely semiconductor. We are not adding any other things from outside, right? Yeah, I hope things are very clear. Let's continue the journey. Yeah, I hope class is going good. So let me remove these things, right? If you have any problems, please let me know. You will be watching here, right? Yeah, let me continue. Next, what we are going to learn, that is we need to learn some other basics. Other basics in the sense, what is the difference between drift and diffusion, right? We have to know the difference between drift and diffusion. First of all, what do you mean by drift? ட்ரிப்ட் அப்படின்னா என்ன அப்படின்னா, ஒரு மெட்டீரியலுக்குள்ளே வந்து எலக்ட்ரான்ஸ் வந்து அதிலே இருக்கும், ரேண்டமாக அதிலே இருக்கும். அந்த எலக்ட்ரான்ஸ் வந்து என்ன ஆகிட்டு இருக்கும் அப்படின்னா, எந்த இடத்துல எலக்ட்ரான்ஸ் வந்து அதிகமாக இருக்கோ அந்த இடத்துல இருந்து எந்த இடத்துல எலக்ட்ரான்ஸ் வந்து கம்மியாக இருக்கோ அந்த இடத்துக்கு வந்து ட்ராவல் பண்ணிட்டு இருக்கும். தட் இஸ் we are simply calling it as drift, right? அப்போ drift current அப்படின்னா what do you mean by drift current? It means electrons are usually traveling from higher concentration point to lower concentration point, right? For an example, if you are selecting some material, right, one second. If you are selecting some material, okay sir, I am having some type of material, right? In that material, in one zone we are having more electrons. In one zone we are having more electrons, right? Whereas in the another zone we are having very less number of electrons. Such that your electrons are started traveling from high electron point to lower electron point. That is, electrons are traveling from higher concentration point to lower concentration, right? Lower concentration point without any external electrical field. Without external field, that is very much important, right? Without external field, that is simply called drift, right? We are calling it as a drift velocity, right? So this is called a drift and its correspondent. Once your electrons are moving from one point to another point, there might be some flow of current, but your electron, that is your current, will be in the opposite direction to what? Electrons. If your electrons are traveling from left side to right side, then your current will flow from what? See, I am taking positive current, don't think too much, right? I am taking positive current means it started following the direction of whom? Positive charge carriers, right? So your electrons are going from higher concentration point to lower concentration point, whereas your current is traveling in the opposite direction, but it is very less amount of current. This is simply called drift current. Drift current in the sense, whenever in case of, that is the internal property of the selected material. In a material, right, if you are having, right, if you are not having equilibrium state, in a selected material, if one zone is having more electrons and another zone is having very less number of free electrons, under that situation, electrons are started traveling from higher potential point to lower potential point, that is high concentration point to lower concentration point. Under this under this condition, your material will experience some flow of current. That current is simply called drift current. Now, what do you mean by diffusion, sir? Then, what do you mean by diffusion? The second case is diffusion in the sense, with the help of external field, if you are trying to move the electron from one point to another point, then that is called diffusion current. It means, sir, before applying the electrical field, my electrons are randomly moving. Now you are supposed to apply some external electrical field such that your electrons are oriented together, right? They might start traveling in a proper way in the opposite direction to the flow of current. They are simply called what? Diffusion current, right? Under this situation, your diffusion current will go in this direction. Why your diffusion current is going in this direction? Why? Because it is what? It is in the opposite direction to the flow of electrons, right? If you are applying the electrical field in this direction, then your current is started flowing from what? Higher potential point to lower potential point. Current will flow from higher potential point to lower potential point. Electrons will started flowing here. I am talking about concentration. I am talking about concentration in the sense how many electrons are there inside the material. Suppose here you might have 10 lakhs electrons, here you might have only 10,000 electrons. Then your electrons are started moving from high number of concentration point to lower concentration point. This case will be different from this one. Whereas in this case, we are going to consider what? Higher potential point and lower potential point. In this case, current is usually started traveling from higher potential point to lower potential point. I hope things are very clear. That is how we are finding the direction of the current in case of semiconductor materials. I hope things are very clear now, right? So this is the difference between drift and diffusion. So drift in the sense without applying the external field, because of the concentrations of the electron inside the material, you can experience the flow of current is called drift current. With the application of external electrical field, right, your randomly aligned electrons are strictly started following a particular direction because of this external electrical field. Under that situation, you will experience some current. That current is simply called diffusion current. That's all, right? There are no more things to discuss here. Now let us discuss about the basic materials. Now we are going to design some type of positive material, and we are also going to design some type of N type of material. Listen guys, first of all, what is the difference between P type of material and N type of material? Let me show you the difference. First of all, if a material is represented as P type of material, right, it means that material is having more number of positive charges. It is having more number of positive charges. It is having more number of positive charges, right? It is having more number of positive charges. Here the doping concentration of the positive charges, right, that is N denotes the concentration, right? So doping value of the positive charge carriers is much greater than the value of doping concentration of negative charges. Clear? Here the small n denotes the negative charge, small p denotes the positive charge, right? So n denotes the concentration, number of charges that is presented in the selected material. If your material is simply called p type material, it means that system is having more positive charge carriers. Holes, more positive charges are being presented there. Similarly, if your material will be represented by n type. N type in the sense the material that we are choosing right here, it is simply called what? It is having more negative charges, right? It is having more number of negative charge carriers. This system is having more number of negative charge carriers. It is having more number of negative charge carriers. Under this situation, negative charge carriers are more in the sense I can say more negative charge carriers, which is always greater than the value of much greater than the value of the concentration of negative charge carriers, or the number of negative charge carriers are much greater than the value of number of positive charge carriers. Clear? Yes, right? So usually it will be represented in three ways, right? Listen, the first thing is, suppose if it is sometimes in your layers we are using P plus, right? If your material is represented by P plus, that is called what? Heavily doped material. That material is heavily doped by positive charge carriers. Plus denotes heavy doping, right? It is called heavy doping. It means I am selecting some material. In that material we are providing more amount of positive charges externally. That material has been externally doped by positive charge carriers. It means that selected material is heavily doped by positive charge carriers. It has more number of holes, right? Now there is another case, P minus in the sense medium charge carriers. It will be represented by medium in the sense what? Sorry, it is not medium, that is low concentration, right? P minus. If it is simply represented by P, then that is called moderate. If it is P, then that is called moderate. Without minus, that is minus or plus. If it is simply represented by P, then that is called moderate amount. Okay sir, அதிகமாவும் இல்ல கம்மியாவும் இல்ல மீடியமா இருக்கு. That is medium, moderate or medium. Whereas low means P minus in the sense positive number of charge carriers are very less. That material is having holes, but that number of holes are very less. Right, that is very less. Similarly, in N type of material, if you have N plus, it means that the selected material is heavily doped by negative charges. Suppose if it is N minus, then the selected material is having very less number of negative charge carriers. If it is N, then that is called moderate number of charge carriers, right? So that is the difference between positive charge carriers and negative charge carriers. I hope things are very clear now, right? Yes. So this is the basic difference between P type of material and N type of material. Right, now what we are going to do, in order to design the applications or analog switches, we are going to combine these two materials to design the switches. We are going to combine these two materials to design the switches. Let us see how to design the switches at all, right? How to design the switches at all. Yes, let me continue. Class is going good, huh? I hope class is going good. With the hope, I'm just continuing the classes. Okay, fine. So next, now what we are going to understand, right? So basically, we are going to learn some basic properties of first type of material. That is, we are going to design PN material. That is simply called PN junction material. That is simply called a diode. We are simply calling it as diode, right? Later, first we will understand the basic operation of diode, and then we will see the application of diodes, and then we will see the application of transistors, how to design the transistors from the diode, and then we are going to see the application of transistors. With the help of transistors and the diode, we are going to design operation amplifier, and then after completing all these sessions, immediately we are going to design oscillators and MOSFET. These are all the whole syllabus of your analog electronics, right? Yeah. So let me start with the PN junction material. That is, we are simply, people are calling it as diode, right? So that is normal diode, right? We are going to design normal PN junction material, right? What do you mean by PN junction? We are going to take two layers, one is P, another one is N, and strictly we are going to join them together, right? I'm just going to join them. This is called a barrier. This is called a barrier. In one side I'm going to use P type of material, and in another side I'm going to use N type of material, and I'm going to strictly join them together to design the semiconductor materials, to design the semiconductor what I can say switches, right? Yeah, let us continue the operation. Anyway, in case of P type of material, I told you it is having more number of positive charge carriers, whereas N type of material is having more number of negative charge carriers. So positive charge carriers are being represented by, right, these positive charge carriers is ready to donate what I can say holes, right? Positive charge carriers are ready to, they are ready to donate the holes, or I can say they are ready to accept the electrons, right? So usually we are calling it as acceptor. Why? Because we are defining all the things in terms of electrons only, right? So electron in, see, wait a minute. If you have positive layers, right? Positive layer is ready to accept the electron, so it is simply called acceptor. We are simply calling it as acceptor. Whereas your negative material, right, it is with the electron, it is waiting to donate the electron. It is called what? A donator, right? So it is called a donor. We are simply calling it as donor. Donor means a material is waiting to provide the electrons to someone, whereas acceptor means a material is waiting to get the electrons from someone. So we are defining these terms with the reference of electrons, right? If a person is giving the electron, then that person is called a donor. If a person is accepting the electron, then that person is called acceptor. Getting me, right? So these names originated with the reference of what? Electrons, right? So the conclusion is what? Donors are readily, right? So they are waiting to donate the electrons, what I can say, whereas holes are ready to accept the electrons. So it is simply called acceptor and a donor, right? So here in case of P type of material, usually your charges are being represented as, let me take P type and N type of material. Let me increase the size of the material slightly to understand the operation much better, right? Yeah. Let me simply demonstrate. I told you I am skipping ESE syllabus, right? Because of time being. In future, if time permits, definitely I will take that. I will cover that ESE topics also, but I don't want to do that one right now, right? Yeah. Let me take. This is our materials now, right? Okay. Later we will connect the battery at all. Let us take. I am taking. I told you this is P type of material. This is called barrier. This is simply called barrier, potential barrier. We are calling it as potential barrier. We are calling it as potential barrier, right? Anyway, let us continue. I said here I am going to use what? P type of material. That is simply called P type of material, and this is going to be N type of material, right? Yes, PN junction diode. We are simply calling it as PN with a junction. It is called PN junction diode, right? Yeah. So let us continue. The next thing is, in case of P type of material, we are having more number of electrons, right? That is more number of positive charge carriers, not electron. Here we are having more number of positive charge carriers, right, to provide, that is to accept the electrons. This person is waiting, actually this person is waiting. Whereas if you observe, right, if you observe N type of material, what your N type of material is going to do? In case of N type, right, this material is readily waiting, right? It is readily waiting to donate the electrons, right? It is readily waiting to donate the electrons. 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 Yes, that is the representation of positive and negative charge carriers. Now actually what will happen? The thing is, when we are trying to join these two materials together, right? So there is N material and P materials are going to be joined together. Now see, when the moment you are joining, immediately this is the joining point. In this joining point, if you observe, right, nearer, that is from the neighbor point or from the nearest point of your selected junction or your joining point of the junction, we may have some charge carriers. Those charge carriers, listen, here we have some amount of charge carriers, they are lying nearer to the junction. We have some amount of holes, this is also lying nearer to the junction, right? And the distance between these two charges are very less. Because of this very less amount of distance, these electrons will try to ionize, or in the sense it will try to donate the electron to the positive charge carriers. It will try to donate the electrons to the holes, such that what will happen, there will be a process of, right, there will be a process is simply called ionization process. Why it is ionized? Listen guys, listen. நீங்க p type of material n type of material கரெக்ட்டா ஜாயின் பண்றீங்க இல்லையா, அந்த ஜாயின் பண்ற பாயிண்ட்ல என்ன ஆகும் அப்படின்னா, இத ஜாயின் பண்ற பாயிண்ட்ல ஒரு பக்கம் எலக்ட்ரான்ஸ் இன்னொரு பக்கம் வந்து ஹோல்ஸும் இருக்கும். அவங்க ரெண்டு பேருக்கு நடுவுல இருக்க டிஸ்டன்ஸ் வந்து ரொம்ப கம்மியா இருக்கிறதால அவங்க என்ன பண்ணுவாங்கன்னா, ஈஸியா இந்த பக்கம் இருக்க மெட்டீரியல்ஸ் வந்து எலக்ட்ரான்ஸ் வந்து டொனேட் பண்ணிடும். So that is called ionization process, right? So that is called what? Neutralized themselves. I am donating the electrons to the holes, right? Because of the less amount of distance. In resultant, what will happen? They will be neutralized themselves, right? So there will be a barrier, right? This potential barrier will be created. How? That is how the potential barrier is being created nearer to the junction, because of this donation, right? Now it will become, what I can say, it will be neutralized, right? It will be ionized. Now if you observe, right, rest of electrons and holes might try to make this same, what I can say, they may try to pair to each other, but it is not possible because your distance is very high now, right? Now randomly, listen, actually inside of this semiconductor material we are having some free electrons and free what I can say, holes, right? If the distance between the electron and holes are very less, then they will combine together. Suppose if your distance is very high, then they won't combine. That's all, right? That is, there are no more things to discuss. So anyway, now barrier is being created here. Now rest of electrons and positive charge carriers are waiting to, what I can say, pair each other. But how it is happen now? In order to make this continuous conduction here, we have to apply external field. Now the first process that we made here, it is simply called a drift process. This is called drift process because without applying any external what I can say, signal, there might be a combination, right? We can observe there might be some slow flow of electron, that is called what? Drift current, right? See that these electrons are started moving toward, that is in this direction, electrons are traveling in this direction. It means positive charge carriers are what? Accepting the electrons. These four layers are donating the electron, these four guys are accepting the electron. They are called acceptor. These four people are called what? Donator, right? So under this process we can observe some type of current. That current is simply called drift current, right? Now with the application of external electrical field, let us see what will happen, right? So this is the basic process of joining p and n material. Immediately after joining p and n, this is what will happen inside the material. Next, if I will apply external electrical field, external electrical field in the sense, here I am going to provide positive supply, here I am going to provide negative supply. Listen, this is positive and negative. It means this positive supply will going to pass more amount of positive charge carriers, and this negative supply will going to pass more amount of negative charge carriers in this direction. Electrons are always traveling in the opposite direction to the flow of current. See there, this battery will going to pass some voltage, right? That is, it will going to pass some current. That current is what? It will always follows the direction of positive charge carriers, whereas electrons are strictly traveling in the opposite direction to the flow of current, right? Yeah, your current is started flowing into this direction, but immediately you cannot experience the current flow. Let's see what will happen when the moment a battery positive terminal is connected with the p. See there, p type is connected with the positive terminal, n type is connected with the negative terminal. Let us see what will happen. Now we all know positive and positive charge carriers, right? Actually this is what I can say, let me take wait a minute. This is positive charge carriers, this is positive charge carriers. Positive and positive charge carriers are will going to what? Repel each other. So what will happen here, when you are applying more amount of positive charge carriers, this all positive charge carriers will going to repel these positive charge carriers. Already we have positive charge carriers, again we are injecting more amount of positive charge carriers, such that the repel force is keep on increasing here, and they are started going, these all charge carriers are started traveling towards the junction, and they are going to collide, that is they are going to hit the junction. Similarly, here we are passing negative charge carriers. Already here also we are having negative charge carriers. Negative charge carriers will repel each other. Because of that, the rippling force is keep on increasing. That rippling force will going to what? This charge carriers will going to hit the junction. So now what will happen? I am keep on increasing the value of voltage. I am keep on increasing the value of applied voltage such that more amount of force will be generated. That because of, see there, we are increasing the rippling forces, right? That repulsion will keep on increasing, so that rippling force will going to keep on hitting the junction to break. Then what will happen? Immediately, if it is the silicon type of material, when the level of the voltage is keep on raising to 0.7, that is the point is called cut-in voltage. Exactly at the cut-in point, your layer will going to be break down and your positive charge carriers started collaborating, that is combining with the negative charge carriers, and you can experience the flow of current inside the device. That is simply called forward conduction of the PN junction. I hope things are very clear. Listen, at very first what I have done, I took P and N type of material, I strictly joined them. I have just started joining them together such that exactly at the junction point, what will happen? In one side we have positive charge carriers, in another side we have negative charge carriers. They have started, what I can say, this negative charge carriers are donating the electrons, positive charge carriers are accepting the electrons, such that one side, that is nearer to the layer, what happened? Your charges are being ionized. Only one side, right? That is only one certain portion, some distance. This is called barrier now. Now, when we are applying the external field, during this application of external field, suppose if your positive terminal is connected with the P type, negative terminal is connected with the N type, then what will happen? Positive charge carriers will going to repel the positive charge carriers, negative charge carriers will going to repel the negative charge carriers, such that both the charges are going to hit the junction continuously. That portions keep on increasing. So after a certain time period, they keep on, what I can say, they are going to hitting the what? Junction. That junction is keep on what? It is going to be weak now. It is getting weak, more weak. Again, I am keep on increasing the voltage. Suppose if it is a silicon type of material, when the level of the voltage will be reached, bumped to 0.7, that is the point where junction is going to be breakdown and your diode is started, what I can say, conduction. That is the combination, that is the charges are going to what? Combine each other. Positive charge carriers are going to be combined with negative charge carriers, such that you can observe positive charge carriers are keep on started traveling in this direction, negative charge carriers are start to keep on traveling in this direction. You can experience the flow of current inside the device, that is called forward bias. Getting me? Let us discuss about reverse bias in the same material. First, now what do you mean by reverse bias? Reverse in the sense, I have to do the same process in the opposite direction, right? Yes. Now let me take the same material. But now I am going to do the same process in the opposite direction. Opposite in the sense, your material will be connected in the reverse direction. It will be connected in the reverse direction. Now we know already size of the layer is increased because some particle is ionized when we are joining P material with the N material, such that this is the new size of your layer. Now in one side we have electrons. Let me directly write. We have electrons. Simply I will write like this. In another side we have positive charge carriers. We know how to represent the positive and negative charge carriers, right? So for your for time being, I am directly writing like this. Now what is the conclusion? Listen. Now positive charge carriers is connected with the N type of material, negative supply is connected with the P type of material. Now we know positive and negative will attract each other, such that what will happen? This listen guys, listen, this positive charge carriers are started traveling in this direction. Negative charge carriers, listen, here also positive charge carriers and negative charge carriers will attract each other, such that all negative charge carriers are coming out. Now what will happen? This potential barrier will keep on increase or not? Why? Because there is no electrons, there is no movable electrons. All the electrons are started going out. If all the electrons have started going out, then the barrier will keep on increase, right? There is no charge carriers, all the charge carriers are started going outside. So the barrier of majority charge carriers is keep on increasing. I am introducing the next term, that is called majority and minority. Right, sir, what is the difference between majority charge carriers and minority charge carriers? In case of P type of material, the majority charge carriers are holes. In case of N type of material, the majority charge carriers are electrons. Now you should should try to get the meaning of majority. Majority in the means, இப்போ நம்ம எலெக்ஷன்ல வந்து மெஜாரிட்டி பர்சன் வந்து யாருன்னு சொல்லி எலெக்ஷன்ல வந்து யார் வந்து ஓட் வின் பண்றாரு அப்படின்னு அனௌன்ஸ் பண்ணுவாங்க இல்லையா? So what do you mean by majority? Number of people voted that person, right? Voted for that person, selected person, right? How many votes are there? Based on the counts, we are choosing the majority and the minority. Deposit அப்படின்னு சொல்லுவாங்க, right? So the conclusion is what here? The thing is, in case of P type of material, we are having more amount of positive charge carriers, right? If number of count is very high, then there is called majority. If count of charges are very less, then that is called minority. In p type of material, majority charge carriers are positive, minority charge carriers are negative. Listen, p type of material majority வந்து positive charge carriers ரொம்ப இருந்தாலும் negative charge carriers இருக்காதுன்னு நம்ம சொல்ல முடியாது. There will be some small count of negative charge carriers. Similarly, in n type of material we have plenty of negative charges. It does not mean that there is no positive charges. Of course, there will be some small amount of positive charges, very less count of, that is very less number of negative charges also will be there. What is the conclusion? Right, in a selected material, majority defines the number of, that is the concentration of the material. If a material is having more negative charges, then that is called what? The majority charge carriers are negative. If your material is having more positive charge carriers, then the majority is what? P, right? Then what is minority? Opposite to P, right? In P type of material, P is majority. In N type of material, N is majority, right? Then which is minority? In P type of material, negative charge carriers are minority. In N type of material, positive charge carriers are minority, because we have very less number of count, right? So like that, listen, all the majority charge carriers are started coming out. But the problem is, I told you in n type of material we have minority charge carriers, right? Now here if you observe, layer of majority charge carriers is keep on increasing, whereas layer of minority charge carriers will keep on decrease. So you can observe the flow of reverse saturation current, right? So let us coming back to the conclusion. Here actually this is the layer. When we are connecting the diode in reverse bias, all the majority charge carriers are started flowing in the outside direction, that is in outward. But if you observe strictly in case of n type of material, you can observe there is small amount of some very less count of positive charge carriers. Here some very less count of negative charge carriers are available. Now see there, this negative charge carriers and this negative charge carriers will repel each other. These positive charge carriers, this positive charge carriers will repel each other, such that this positive charge carriers started penetrates towards this direction, and this negative charge carriers started penetrating towards this direction. And see there, current is always started flowing in the direction of what? Positive charge carriers. Since minority charge carriers are started penetrating in this direction, but minority positive charge carriers, minority positive charge carriers are traveling from n type of material to p type of material, and your current also started traveling in this same direction, that is called reverse offset saturation current. I told you, right? So reverse offset saturation current, in the sense during the reverse bias, all majority charge carriers are coming out, right, coming outside, such that the barrier of the positive charge carrier, that is the barrier of majority charge carriers will increase. Barrier in the sense we are creating, yes, what I can say, நம்ம என்ன பண்றோம் அப்படினா we are creating a big dam, like that. That is, இங்க நான் என்ன பண்றேன் அப்படினா we are putting the barrier for the flow of what? To stop the flow of electrons towards what I can say, towards p type of material, because we are collecting them outside, we are collecting this one also outside. But the thing is, this layer is increasing for whom? Majority charge carriers. Whereas in the opposite case, the another side, right, one more layer is decreasing. That decreasing layer means the minority charge carriers layer is decreasing, majority charge carrier layer is increasing. Getting me? அப்ப என்ன ஆகும் அப்படினா, you can observe the minority reverse saturation current, it will be in nanoampere, right? It will be in nanoampere, right? So let me define. Actually we saw the general definition. Diode current id is equal to reverse saturation current, offset current I naught into e power diode voltage upon eta times of vt minus 1, right? Now in forward bias, the value of id, right, in forward bias, id is equal to approximately equal to the value of I naught into e power vd upon eta times of vt. Why? Because whereas the value of vd is positive, right, diode voltage is, the voltage drop across the diode is positive, and I can say the value of e power vd upon eta times of vt is far away from the value of 1 in case of forward bias. In reverse bias, the voltage drop across the diode is negative, right? See the opposite voltage, reverse bias, right? In reverse bias, right, the voltage drop across the diode will become negative, such that we can say e power minus vd upon eta times of vt, it will become negative, and this value is much less than the value of plus 1. If it is less than plus 1, then if you take this equation, then this diode current approximately equal as id is approximately equal to I naught into, see there, this term is neglected now, this term is neglected, and we are going to consider only minus 1, so it will be approximately equal to minus I naught. So reverse saturation current, why it is minus I naught? Why? Because it is traveling in the opposite direction to the forward current. Usually your current is traveling from p type of material to n type of material. It means this is called anode terminal, this is called cathode terminal in our diodes, right? So usually your charges are flowing from anode material to cathode material, right? That is anode to cathode. But here your current is started traveling from cathode to anode. This is opposite direction to the, again, that is this direction is opposite to actual direction, right? So that's why we are putting minus, that's why we are getting minus here. So reverse saturation current means minus I naught, right? So that is in negative, that is in reverse bias, and this current will be in nanoampere. It is very, very less. So what we got here, this diode almost it will be conducted in forward bias, right? Yes, and it won't conduct in reverse bias. Majority charge carriers won't conduct in reverse bias, but minority charge carriers will conduct. They will pass some what I can say nanoampere current. That current will started flowing in the opposite direction, but strictly that current is almost equal to zero. We are not giving that, but it is insignificant. We can say that value is what? Insignificant. See, the beauty is here I had selected what? The material that I had selected here, it is called what? Silicon type of material. I'm not going up with the germanium type of material, right? Now here I would like to define few more things here. Listen, this I naught is reverse saturation current, Vd, that is the voltage drop across the diode, and this eta, it's this zeta, that is the epsilon, or we are calling it as eta, many names are there. Anyway, let me call it as eta, right? So eta means what? Ideality factor. That ideality factor is 1. Strictly according to our syllabus here nowadays we are following it as, it value is 1, right? Its value is 1, but according to the fundamental theory, at very first when this origin were started with the silicon and germanium material at all, for germanium this eta value is 1, for silicon it is 2, for silicon it is 2. Now you might be think, sir neenga silicon thana use pannirukeenga, appo yen neenga eta ku vandu 1 eduthinga. Actually nowadays we have modern technology. With the help of modern technology, the structure of the material had been improved a lot. It means we are having smooth material. In smooth material, though we are designing the material with the help of the silicon, almost the value of eta is what? It has been minimized to 1. But when we have started, that is the first where the materials were invented, under that condition this ideality factor had been defined as 1 for germanium and 2 for silicon. Anyway, if it is given in your examination, then you can strictly follow. Ideality factor is given as 2. If it is mentioned like that, then you can consider. Unless otherwise the value of ideality factor is 1. I am repeating once again, though we are using silicon material in your examination, unless they mention the given value of, that is unless they mention the value of ideality factor, don't take this value as 2. Just to strictly consider this value as always 1. If it is given as 2, then take that one. Value வந்து 2 அப்படினு சொல்லிட்டு அவங்களே கொடுத்திருந்தானா எடுத்துக்கோங்க. இல்லாட்டி இதோட வேல்யூ வந்து 1 தான் for all type of material. It might be silicon or germanium. Getting me? Yes. So this is all about ideality factor, right? Now here Vt stands the thermal voltage, right? It is stands the thermal voltage, and the value of thermal voltage is approximately equal to 25 millivoltage. Some people are defining it as at 26 millivoltage also. Anyway, while solving the problem, I am requesting you please to take 25 millivolts, right? Some people are using, that is there might be some another reason for that, why we are taking 26, why we are taking 25 millivolts at all, but I told you strictly I am following its syllabus, right? So there are many other things are there in engineering syllabus, that is ESC point of view, right? Yes, let us complete. Just to take thermal voltage is what? Only 25 millivoltage, right? Okay, now another thing is, if your selected material, semiconductor material, is a very good semiconductor device, if it is a semiconductor device, very good semiconductor device, then it has to conduct at a normal room temperature. ஒரு மெட்டீரியல் வந்து சூப்பர் செமிகண்டக்டராக இருக்குது, இது ஒரு நல்ல செமிகண்டக்டர் டிவைஸ் தான் அப்படின்னா, நார்மல் ரூம் டெம்பரேச்சர்லேயே அது என்ன பண்ணலாம், நீங்கள் வந்து கண்டக்ட் பண்ண வைக்கணும். அதுக்கு வந்து டெம்பரேச்சரை இன்க்ரீஸ் பண்ணாதான் அது டர்ன் ஆன் ஆகும் அப்படிங்கிற சிச்சுவேஷனுக்கு வரக்கூடாது. தட் இஸ் வெரி குட் செமிகண்டக்டர் மெட்டீரியல், ரைட்? எ நார்மல் செமிகண்டக்டர், எ வெரி குட், ரைட், வி கேன் சே எ வெரி குட் செமிகண்டக்டர் டிவைஸ் வில் ஆல்வேஸ் கண்டக்ட் அட் நார்மல் ரூம் டெம்பரேச்சர். கிளியர்? ஸோ திஸ் இஸ் ஆல் அபவுட் வாட் ஐ கேன் சே பேசிக் ஆஃப் PN junction diode. I hope the things are very clear now. So what we have done till now, we understood the basic, right? So in analog electronics, I said there are 3 type of materials. One is insulator, another one is semiconductor, another one is conductor. Now anyway, switches are going to be designed with the help of semiconductor. Under semiconductor we have 3 type of classification. Silicon is there, germanium is there, and gallium arsenide will be there. But which material we are going to use? We are going to use silicon and germanium, whereas gallium arsenide will be used in case of what I can say CMOS technology, that is complementary MOSFET, N MOSFET, P MOSFET. There we are giving priority for gallium arsenide because of high switching speed, or I can say mobility of gallium arsenide is very high when we are comparing it with the silicon and germanium. Anyway, to design our switches, we are giving priority for silicon and germanium only in the electron voltage point of view, right? See, electron volt in case of silicon and germanium is only 1. When we are looking, that is when, sorry, I cannot say, I given some values, right? For germanium it is 0.7, for what I can say, for silicon it is 1.2 around, whereas for gallium arsenide it is going to be 1.85. So out of these 3 electron voltages, silicon and germanium are having very less less amount of electron voltage to release the free electrons. So priority will be given for those two materials in the electron volt point of view. So second category, under silicon and germanium, priority will always be given for silicon, right? That will be, there are three categorization. It is depends on the cut-in voltage, temperature, and reverse saturation current, right? So these three properties of silicon material is very good. So that's why we are giving priority for silicon material to design the analog switches, right? So next, what we had been discussed about what I can say, reverse saturation current, drift, diffuse, right? Now, and then we took p type of material, n type of material, and we saw the difference between p and n type. Now I had been merged them together. This is p and n, and we saw the basic operation of p-n junction diode. It is simply called p-n junction material, or this process is called p-n junction process. And here we understood this is the basic simple operation of diode. And from here we are going to collect many observations, like we have to design forward characteristics, reverse characteristics, that things at all we will see in our next class, right? I hope things are very clear. If you find any doubts or if you have any issues, you can ask in our group, right? With this, let's wind up the class. Thank you all.